The 9/11 scenario, where one has an impact, followed by fuel dispersion, followed by a fireball, followed by structural heating, followed by structural collapse, is filled with science problems that we don't yet fully understand. An area of intense interest is the water fuel dispersion problem. Here we are trying to understand the mechanisms that lead to a dispersion of a liquid at 4 to 6 times the impact velocity, resulting in fuel breakup that could lead to ignition. This is fundamental research that will find its way into our computational models and improve our predictive capability in these combined environments.
Sandia National Labs has been involved in several large-scale tests looking at fuel impacts onto structures. What we learned from these tests is that there's a missing link. There's an area of research that we don't understand. We don't know what happens to the fuel when it hits and disperses. We know what happens to the structure when the fuel tank impacts, but we don't know where the fuel goes or what happens to it. So from these tests, we started doing research at various scales, looking at the impact of fuel or any liquid hitting a wall at high speed and then dispersing or splashing. And we've gained a lot of understanding through this research using various techniques such as laser diagnostics, high-speed photometrics to understand what happens to the liquid as it splashes and try to figure out where does it go, what size is the splash going to look like. So what we're really interested in looking at is where does that fuel go and what state is it in? So we can run some models and simulations on how it's going to burn and how it's going to affect the structure in later time. So what we're doing is we're doing tests at various scales. We're doing tests where we're doing simulations of full-scale fuel tanks hitting structures, all the way down to tiny droplets hitting structures, and looking at the scale of impact and dispersion of these different liquids and what the state of these liquids are as they impact and disperse. The reason we're interested in this is because of accident scenarios where you have fuel that has an impact, or an intentional scenario from something such as an airplane impacts and disperses the fuel throughout the structure, and you have burning within the structure from that. And this is a missing link that nobody really knows what happens to the fuel, what the dispersion looks like, so you can do any kind of a fire simulation later on based on the state of that fuel and the dispersion of that fuel. Because this is really an area where there is no data, it's a kind of a discovery type of experiment where we're looking at the impact and dispersion of different liquids. And from this we've developed a lot of new theories and formulas to help us understand how the fuels disperse, what the state of these fuels are as they disperse. So when you input these into a fire simulation, you have something to start with, so you can run your fire model and run some other fire tests and understand what the thermal response is of the building. And if we get that data, we can use that data to input into fire simulation models, so we can understand how the fire is going to behave and if it's going to explode or if it's going to burn for a long time. And by doing that, we get the idea of what the thermal response or the heat response of the structure will be on top of the initial impact from just the fuel tank itself.